Folks, so in this video we're going to explore at least from a very high level finally what are type classes in Haskell. And the best way, the best way, at least I believe, and the way this has been introduced typically in many literature and textbooks on Haskell is that a type class is, think of a type class as some kind of an interface. Okay, so let's say I have some kind of an interface over here. Okay, and I'm just going to give it a name. Let's just give it a name to this interface here. So I'm going to call this. So let me use a slightly different color here. So let's call this as EQ. Okay, so I've got my interface over here, and I'm going to give it a name, which is, let's say, EQ. And this interface or this type class, okay, it just from a very high level, it just defines some specific behavior. Okay, it's not going to define how that behavior is going to work. Okay, it's just going to define what is that behavior. All right, and so let me be a little bit specific. What do I mean by behavior? And let me just explain this a little bit more clearly. So I have an interface over here, and I've given it a name EQ. And if you're coming from a Java world, you might think of an interface as something that has a set of abstract methods. So let's take that analogy, and let's say that this type class EQ in Haskell has a set of abstract methods. So let's say it has a function 1 there, it has a function 2 there. Okay, now I do not know how these methods have been implemented. Okay, all I'm just defining here is just the behavior, and one of the functions could be, I don't know, it could be, let's say, the equal to. Okay, and the other could be maybe the not equal to. All right, so with the equal to, I'm specifically saying that the behavior of equal to is that it takes in some value, okay, associated. Now remember, I'm right now in the type one. I'm trying to define the type. I'm trying to define a type for my equality method. And the way equality works is it takes in some value associated with this type associated with this type variable A, takes in a second parameter, and then it gives you back a boolean value. Okay, and simply not equal to, it takes in two parameters, and then it gives you back a boolean value. And now the question with type classes just comes down to the simple idea that if you have any type, if you have any other type in Haskell, it could be a type integer, a type float, a type character, any type, you may have created a custom type, right? If any type that you happen to have in Haskell that would like to support these behaviors, then that type must be must become an instance of this type class EQ. Okay, so again, if I were to have, let's say, some custom type, let's say I created some custom type in Haskell saying data, I don't know, own my own type. Okay, and equals to something. All right, and maybe I might have some other types in Haskell, such as an integer, or maybe a float. Okay, or maybe a list of something, let's say a list of integers. Okay, and I would like these types to support the behavior of an equal to method, and should support the behavior of a not equal to method. Okay, the implementation as to what makes two integers equal can be implemented directly within that class over there. But what I'm trying to say over here is that if it would like to support these behaviors, then these types over here, or int, a float, or a list of these things, right? These things must be an instance must be an instance of my type class equality. Okay, now Haskell has many type classes. We're going to look at a few of these type classes, such as a functor, an applicative functor, a monad, and a monoid later in the video. And but right now we're just going to restrict ourselves to something really simple, which is basically the equality, or in this case the EQ type class. And given that, one of the things I can show you this formal definition of this type class by just basically running the info on EQ. And what I get back over here is, if I just zoom in a little bit, I can see the actual definition of my type class right there. It just tells me that if you have any type, which is in this case A, that would like to support the behaviors that are outlined in my EQ type class, and the behavior more specifically are these two, then your type must be an instance of my EQ type class. Okay, so let's do this. Let's try to figure out what is the method, what is the type of this method equal to. Now, given this formal definition of a type class. So if I say what's the type and equal to, I get back that the type on equal to is that, again, it doesn't just take in any kinds of types here. This type that we're talking about in this type variable A is a very specific kind of type that happens to be an instance of the EQ type class. Okay, so if I were to call my equal to method as an infix operator, so let's say 6 equals to 5. Okay, the only reason I get back a Boolean value, so the only reason this actually works out, so the specs of the method tells me that I get back a Boolean value, and the Boolean value is right there the moment I pass in two inputs. Okay, these are my two inputs to my equality. Okay, and so this is the type of my input 1, the type of my input 2, and that's the actual value, and as long as the type, in this case, which is an integer, happens to be an instance of my EQ type class, then this method is actually applicable to work on that type there. Okay, so let's look at a few more examples here. So this is my EQ type class, but likewise I can maybe if I do an info on, let's say, ORD, which we say for ordering, and let's just scroll up over here to see the actual formal definition of my ORD. The formal definition of my type class ORD is basically right here, and again it's simple in a sense that it tells me that the definition is that this is my class, this is my definition for my ORD, but what was being told in this case is, or being mentioned in this case, is that whatever this A is must also belong to the type class EQ. In order for a type to be an instance of my ORD type class, that type must also be an instance of my EQ type class. But again, it has a set of properties. It has a set of methods. That's my function 1. That has my function 2, function 3. That's my function 4, function 5, function 6, and function 7. And if I were to, let's just take one of these methods. Let's just take, for example, the max method. Okay, let's take the max method and see whether I can actually figure out what a type associated with that max is. So if I take the max method, and if I ask Haskell's type inference, what is the type on the max method? Okay, a max method is something that takes in two two input parameters, and it gives you back the maximum. It gives you back the maximum between those two values. But the constraint here is that whatever value that you were to give me, the type that is associated with that value, the type must be an instance of the ORD class. It must be an instance of the type class ORD. Okay, otherwise it just won't work. So if I do a max on 6,7, okay, and let's do this. Now again, this is also my next video is going to be, or the next part is going to be on the show type class, but right now let's use that 6x equals to max of 6,7, and then for to see what's the value on my x. Okay, so uh, so if I tell Haskell what's the type associated with my max method, I can see that it takes in these two parameters and gives you back the maximum between those parameters. So if I do a max between my 6 and 7, okay, I get back that the max on 6 and 7 is 7 here, and the only reason this max works on these integers, on the type integer, is because my type integer happens to be an instance of the ORD type class. Okay, and likewise, let's just do one more type class. Let's just look at one more simple type class, which is the show. So if I do an info on my show type class, I see that my show type class is something that has a certain set of behaviors, a certain set of properties, and these properties are basically these three methods over here. And if I were to, if let's just figure out how would I even use the method show in this case. So if I were to run a type on my method show now, the method show basically takes in some value associated with this type variable, a, as long as the type in that type variable happens to be an instance of my show type class, then out comes back a string. So let's try that. Let's do show on 6, and again, the integer is something that works, is a type that happens to be an instance of my show type class, and that's the reason why I can actually make it work or pass a value that happens to be an integer. Likewise, if I do a show on a list of 1, 2, and 3, okay, I get back that a string representation of this thing. Okay, and likewise, if I do show, let's say, on a tuple, now this would be the string representation of my tuple here. But again, the key idea here is that the only reason I can pass in these values is because the type that is associated with these values happen to implement the type, happen to be an instance of the type interface show.